with that, I would like to introduce today's speaker, Ulrik Günther. Ulrik has a master's degree in physics from the Technical University in Dresden, and he got his PhD in computer sciences at the Center for Systems Biology in Dresden, which is a collaboration between the Max Planck Center for Cell Biology and Genetics and the Technical University Dresden. He is now a postdoctoral researcher at the Center for Advanced Systems Understanding in Görlitz. And his work focuses on bringing biology and augmented and virtual reality closer together to aid the understanding of multidimensional data. And he'll be telling us today about how virtual reality can be used for tracking tasks. So please, Ulrik, go ahead, and we're really looking forward to your talk.
Hey, yeah, thank you very much for the kind introduction and for having me. Welcome to my talk about mainly a recent publication we had at the ECCV conference in bioimage computing last year. It's called Bionic Tracking, and the entire project is about making cell tracking tasks faster and more ergonomic with eye tracking in virtual reality. My name is Ulrik Günther, as Johanna has already told you. I'm with the Center for Advanced Systems Understanding in Görlitz, Germany, and also associated with the Center for Systems Biology in Dresden and the Max Planck Institute for Molecular Cell Biology and Genetics. Okay, so as this is Euro-BioImaging, you are probably all very familiar with all the beautiful images that people can create nowadays with state-of-the-art microscopy, with light sheet microscopes that exceed data rates of several gigabytes per second and are easily able to fill up tons of hard drives. And while it's certainly beautiful and mesmerizing to look at these images, it's usually not the goal, right? You want to extract quantitative data from it. And one of the ways of doing that is like turning images, for example, into cell tracks. And this task, however, is, and I can unfortunately not see all the participants. I hope there's like maybe some, show video panel. Yeah, I can actually see participants. So probably all of you who have done cell tracking before would agree that this process is often not as easy as it sounds, especially if manual tracking comes into play. Then people quickly get carpal tunnel, or you have to hire like a poor bachelor student who will do all your cell tracking tasks. And even with the advent of machine learning or deep learning based techniques for performing such tracking tasks, the manual curation step, or at least a little bit of manual annotation, is still necessary, even if it's just, for creating a little bit of ground truth data in the beginning. So, and just to make things perfectly clear in the beginning, we are not trying to solve cell tracking entirely with this project, but what we are trying to is just make the manual curation or ground truth creation step easier and more ergonomic. So just that we're on the same page here. And one thing that kind of complicates these cell tracking tasks is that you get a large variety of cell shapes, right? You have some things that look a little bit like a flower bouquet, some cells that look a little bit spherical, and some that look like a U or like oblong. And this doesn't even yet get into the problem of maybe uneven fluorescence or one-sided illumination that doesn't give you like a nice clear picture of your cells over your entire field of view. And the data I'm showing here is actually one of the data sets we used for benchmarking in the paper. It's a roundworm, the Platenaris dumeri, that's currently also a research subject in Pavel Tomanczak's lab at the MPI-CBG. And what people are doing so far, so I should have asked for a show of hands again in the beginning, who's been doing cell tracking before. So just to quickly show you, if you are using any of the current cell tracking pieces of software like TrackMate or Mammut, then this is probably what you will do. You will have your image here, and you will start clicking on it and connecting the cells and creating this lineage tree that's shown about in the middle of the screen. Oh, this is it's actually Mastodon. So Mastodon is the successor to Mammut. And thanks here to Jean-Yves Tineves, one of the authors of Mastodon, for providing me with this video. And what you can see here already is for doing this in 2D, you need like separate views on your images to get kind of good overview. And you can see that Jean-Yves is also constantly readjusting like the circles in both the windows to get a good view of the cell. And in this 2D views, it's really hard to comprehend what the actual three-dimensional structure of the cell or of the tissue is. So what can we do about this? So we're thinking about different kinds of modalities for making this easier. And kind of one thing that comes to mind is, I don't know who of you has maybe seen Minority Reports, a cool science fiction film from like early mid-2000s. And there they have this amazing user interface where Tom Cruise is standing there swiping pictures all over the place. It looks really cool. And you could imagine, you know, you take a controller like this one, like a VR controller, and then you start tracing cells. And if you still think this sounds cool, then I would like to ask you to stand like maybe for half an hour like this and see how this feels. This is going to be a little bit of a pain. And especially if there are any climbers with us, they know how hard it can be to hold up your hands even just for a minute. And as a kind of a fun fact for this movie, actually, Tom Cruise, this like probably pretty well-trained guy, had to take pauses every half hour while filming because he was just totally exhausted from holding up his arms. So what are alternative input modalities that could help you with not, you know, shifting around your mouse all the time or keeping your hands Tom Cruise style up in the air? And it turns out that we actually have an excellent tool available, all of us, that is extremely well trained for tracking objects, but it's kind of underused a little bit as an input modality. And what I'm talking about is your eyes. So in your daily life, you will have a lot of situations where you're following around objects. When you, for example, you want to cross a street, you're trying to follow a car. Your eyes can do that super easily. Try to make a computer follow a moving object. People are still struggling with that in cell tracking or in autonomous vehicles. It's a super difficult problem. But if I tell you once, you know, this is the object you need to follow, you can do that, no problem. And this is what we're actually doing next. So this is usually more fun if you can actually see the audience. But you have to promise that you will try it for me. So have a look at this blue circle there and follow it with your eyes. No problem, right? You can easily follow it, and it's almost effortless. So what you've just been doing is one of the eye movements that your body is able to do. There's kind of two major categories. There's like this kind of jumpy thing that you see in the left-hand side video, and this one is called a saccade. And you perform these movements also all the time when searching for a new stimulus in the scene. So when you're just looking around, your eyes move super fast, often exceeding angular velocities of 1,000 degrees per second, while looking for something new that you can focus on. And the things you focus on are usually things that have a high contrast, that are somehow different from the background. The other thing that's super important is the smooth pursuit eye movement. And this one is extremely interesting also in terms of all the brain regions that are involved in controlling it, because smooth eye movements are actually not possible without a stimulus. So you can try, looking at a totally blank wall where there's nothing that stands out, and you will find that it's absolutely impossible to perform a smooth movement. Your eye will always perform a saccade focus on something, even if you're making it up. So, but if I hold up my finger and tell you, follow this, it's no problem. You can easily do that. And even Oh, I actually been lying to you a bit. So these are not the two things that are the only things your eyes can perform. There's also other things. There's microsaccade. There's the vestibular ocular reflex. If you're curious about the details, actually have a look. For example, in Dukovsky's book, there's a super comprehensive manual to eye tracking. And maybe a word about the vestibular ocular reflex. This is kind of the thing that kicks in when you're moving your head, that tries to kind of stabilize the image so you don't get sick. So it's also another very interesting systemic thing that involves a lot of brain regions and also like the auditory areas of the brain for that are involved in balance usually. Okay, now let's try a little bit of more complex path and try following this dot again around with your eyes. I hope this is not too choppy in the transmission. So you can see this one is now taking not a straight path, but it's moving more a little bit in an oscillatory fashion, but you are still able to follow this around. So no big deal. And let's have a third try here. And the task for you again is just the same. Look at the blue dot and follow it around. And I would expect that you were not able to do that. So smooth pursuits actually are extremely cool for following things around, but they have two limitations. They have both an onset delay, and they also have a maximum achievable speed. And this onset delay is usually something around like 200, 250 milliseconds before your brain is actually locked onto an object and is able to follow it. And the maximum achievable speed is usually a bit tied to like oscillatory movements. And as soon as something goes like above 2.5 hertz, then you are not able to keep up anymore. And you've probably noticed that when I was playing this oscillatory motion faster than before, that you were locking on to different places, but you were not able to follow the object smoothly anymore. So these are the things that you need to take into consideration when designing anything eye tracking based. And there's actually another thing that, because I have time, I will mention here now. So has anyone heard of the fable of King Midas? Yes? Yeah. So in an eye tracking, there's a famous. Maybe I should actually just tell about the fable first. So this fable is about if I remember correctly, Greek king who had well, probably for a king, rather understandable wish that everything he touches would turn into gold. And while this sounds like a nice idea first, this guy in the end starved to death because, well, try chewing on gold. It's not very delicious and also quite indigestible. So this problem also pops up in eye tracking because you're looking at something, say you use your gaze where you're looking at as a cursor for selecting objects. And your computer usually doesn't know whether you actually looked there intentionally or whether you have been just distracted by something that popped up in the vicinity. And so this is a problem that often plagues eye tracking interfaces. And I will actually come back to that later because, of course, we also have that issue. Okay, so let's continue. So if you want to use an eye tracking based interface, the first thing you have to do actually, well, having eyes helps first, certainly, but you also need to have something that's able to measure where you're looking at. And the first method for doing that is actually this kind of thing that still gives me nightmares. It's called a scleral contact lens. So it's a contact lens that has some coils. And you put the contact lens on your eye and then you have this cable coming out and you put the entire thing in a uniform magnetic field. And I can already see Asta going mad about this technique. So you can imagine this is not like something very comfortable. And there are fortunately less invasive techniques available now. So this is not what we have done. So don't be scared yet. So another thing you can do is electrooculography. This is kind of working the same way as a EEG or as a ECG for actually measuring muscle currents. But here you actually put the electrodes around your eyes and you measure the muscle activity. Again, if you use this in a lab setting, your colleagues would probably laugh at you, even if it's very effective. We have settled for probably the least intrusive way of doing this, and this is a method called video oculography. And it works by having a camera pointed at your eyes, either monocular, as you can see in the image, or binocular, where you have two cameras pointed at your eyes and filming where they're looking at. All of these different ways of tracking your eyes have, of course, different trade-offs. As the scleral contact lenses have a super high setup effort and they are super intrusive, right? Who wants to put I still get chills from it. It's disgusting. It's super uncomfortable, but you get an extremely high accuracy and you get also an extremely high temporal accuracy. And the video oculography that we settled for has a very low setup effort. You need to put on the glasses, you need to calibrate them once, you're done. It's very unintrusive. It's just the same as putting on a VR headset or putting on some glasses. You trade that against a little bit of spatial accuracy, but like having usually like 1 degree is a little bit optimistic, but you get like 1 to 2 degrees spatial accuracy and a temporal accuracy of 2 to 5 milliseconds. And these 2 to 5 milliseconds, they're perfectly fine for us, and they are usually incurred by the image analysis that you have to perform on the video data, because this is of course not entirely latency free. Okay, so let's actually talk about the bionic tracking approach. So what you see here in this image is actually the setup that we've used in the paper. It's a HTC Vive virtual reality headset, and has any one of you never ever used virtual reality before, like a VR headset or anything? If you can maybe click this like raise hand button, I would be curious if there's people who haven't used it before. Okay, so one person. Anyone else? Okay, let me quickly pull out a VR headset. So I can't show you the one with the eye trackers because I don't have that here at the moment. But let me actually quickly show you like a Oculus Quest VR headset. So this is essentially like a little device that contains two smartphone displays, some lenses inside, and you put them on your head and you get a stereoscopic image. And in the setup that I've just shown you on the slide, we have two cameras that are mounted essentially below the lenses, and they are mounted in such a way that you can even use them when you wear glasses. So of course it depends a little bit on the kind of frame you have, but for me, my glasses, they work perfectly fine. And so this entire VR thing has already had kind of a boom in the 90s, but back then, like the entire technology was not as ripe as it is yet. So people were suffering from like low frame rates, and low frame rates in VR means you get sick, and then of course you don't like it anymore. And then people had all these cool ideas like this Minority Report kind of thing for like super fancy user interfaces, and people often said, yeah, you know, this is actually super cool, but can I have a mouse and a keyboard, please? So we have to try to learn from that and come up with better solutions. And this is kind of one of the directions that I believe is very useful. And okay, so let's actually get back to the bionic tracking approach. So what we're doing there is we are tracking the user's eye movements, not actually just the user's eye movements, but the entire user movements plus the eye movements. And we are using a heuristic for the detection of the cell nuclei. And the interesting thing here is actually that your body becomes the user interface. Because when you, I don't know who of you regularly plays like computer games, like maybe 3D shooters, Counter-Strike or whatever. Any gamers here? Nope. Okay, one, yeah. Okay, good. Or maybe you have modeled something with Blender before or done anything like that, and you probably have seen that when you want to move around in a 3D scene, you have to take your keyboard and you have to take the mouse, and it's quite cumbersome. But now imagine you don't need to do that. You have the data set floating in front of you, and you can just walk around it. So your body becomes the controller, right? And you even know where you're looking at. So that's kind of the gist of the technique. And what I should also mention is these eye trackers that we are using in the HTC Vive, they originally come out of an academic setting, but there's has now been formed a spin-off company named Pupil Labs, and you can buy these eye tracking cameras for around €1,000, or you can actually 3D print everything yourself, and the cameras are just off the shelf. So if you want to just do the entire thing on your own, you can do that and just download the software from GitHub. So this is a super low barrier setup, and even I think in terms of lab costs, like €1,000 for eye tracking setup is also pretty manageable. And I think these kind of things will also become more ubiquitous in the following years. So you will probably have a lot of VR headsets with eye trackers coming up. Okay, so as you've come for the bionic tracking thing and not just for me ranting on about user interfaces and eye tracking, let's actually have a look how this looks like. So here we have, these are actually my eyes here, and I'm tracking a cell in this data set here. And you see maybe a little red dot in about the center of the screen. And this little red dot indicates where I'm looking at. And you can see that the eye tracking cameras have locked onto my pupils, so they are able to quite reliably make a determination of what I've been looking at. And there was just an interesting thing here. Let me see if I can find that again. Here, I've been just a little bit distracted, looking a little bit beside the cell. This is exactly this Midas touch problem, right? What do we make of that? I will tell you about that in a moment. But what you can see here now is that the cell that we've actually been tracking, we could create quite a good-looking cell track from it. So now it's calculating, and you can see the cell is nicely moving along the track that I've just been creating by looking at it. And the data set that we've been using here in this trial, this was 101 time points. And the entire time this took me for creating this track was about 30 seconds. So this also works pretty quickly. So let's have a deeper look here. And what you see here is actually, and this was not as well visible in the previous image. So this ray that you can see here, this is actually the ray that connects essentially my head position to the position where I was looking at. And this kind of emphasizes what I mentioned before, that your whole body is essentially the user interface, because you can see that I actually walked, right? I was not standing in a single position, but I was kind of following the cell around by probably moving sideways here. And I think this illustrates it nicely because it was not as well visible in the previous picture. Okay, and so, and this is like what I was able to do after about half an hour. So these are, I think, 52 cell tracks I was able to create within this time. You can see that there are still a few that would probably need a bit of ironing out. But in general, this technique has proven to work pretty well for creating single cell tracks. So let's talk a little bit more about how it actually works. So as said, we do record the gaze, the body position, and the gaze direction of the user. But how do we get actually from the gaze of the user to a cell? So we have all these positional and directional information. We have the gaze direction, head direction, position of the user, position of the head. Now what we do is we sample through the volumetric data along this gaze ray. And then we connect the individual detections that we've figured out by using an iterative graph-based algorithm that I will explain in the next slides. And what we do then is we filter out track segments with a Z score bigger than 2. So this means that we try to avoid this Midas touch problem by the assumption that the cell movement is smooth, which is, I think, a reasonable assumption to make for data sets that have been acquired for the purpose of cell tracking. And what we filter out here are segments between 2 time points that are essentially above double the standard deviation of all the segments in this entire track. And this provides us with a simple yet effective option for removing all segments where the user has been briefly distracted. And believe me, this is going to happen all the time. But with this, we are able to filter this out quite reliably. Okay, now to this graph-based algorithm. So one of the limitations that we have at the moment is that when you start this tracking process, and the way you do this is you take one of these controllers from the VR headset and you push the trigger button. It starts the tracking process. And at this point, you have to be looking at the cell that you want to track. So this is because we have to kind of have an initial seed what you want to track. And then we continue following what the user is looking at. And what I've visualized here in this image are like different detections that lie along this gaze ray where the user has been looking through the volume. And for example, with spine 2, so we call these things with detection spines, you can see that here, for example, there was probably another cell that briefly moved in front of the user while the user was actually looking at the cell behind. But as the world space distance between these 2 detections is smaller than the other one, the algorithm will decide for the middle one here. And this continues with all the other cells. And in the end, we have a full cell track. And should the algorithm fail at some point with doing that, again, as said, this is an algorithm that is very simple. It's not made for being ultimately robust, but it's meant to be good enough. Yeah. And if the result turns out not to be as good, you just push a button, you track the cell again, done. Okay. And for all these kind of user interface things that you need to do, you would usually perform a user study. So this means you give people a certain task to perform, cell tracking, of course, in this case, and you evaluate how they are doing this and how well they tolerate it, right? Because again, coming back to the Minority Report example, if people are exhausted after just doing this for a few minutes, then maybe it's not so good. If people start vomiting after 5 minutes, maybe you need to do something else. So we've conducted kind of a proof of concept study with 7 experts in either manual or algorithmic cell tracking. And we had 1 female participant and 6 male participants. And our goal was to figure out whether people accept eye tracking and virtual reality as an input modality for creating single cell tracks. And the way the study was performed is that the users got an introduction into how the entire thing works. Then there's a little bit of an informed consent part, because sometimes people might also suffer from virtual reality sickness. So you need to inform them about what are the potential dangers of the entire operation. And they have been asked for their well-being before the user study and after the user study. So we could compare whether we had maybe bad influence on how people feel. And then they were able to create as much cell tracks as they liked in this data set that I was just showing you. And for all these kind of things, for these usability evaluations, there are kind of standardized questionnaires. For example, there's the user experience questionnaire and there's the systems usability score. And the NASA has also developed something that's called a task load index. That actually came out of the space shuttle program, where they wanted to know whether a certain interface puts too much mental strain on the person. So you have to perform like 10 tasks, rapid succession. Oh no, and the space shuttle is blowing up, what am I going to do? Right? So people need to take like the right decisions within a short amount of time. Is this putting a strain on you? Is it not? This is what these things are about. And then there's also the simulator sickness questionnaire. And this is exactly for measuring what it says, whether you experience any dizziness, any nausea, anything like that. Okay, so what have we figured out with that? So people were actually quite quickly able to use bionic tracking. They found it intuitive and they could create good quality cell tracks. from their self-assessment. And they could actually imagine using bionic tracking for their manual tracking tasks. And they stated that it provides an improvement in terms of ergonomics and speed over current techniques. And another positive aspect is that we found that bionic tracking did not significantly alter user well-being, and the overall ergonomic aspects were actually complemented by the users. The downside of the thing is that the VR headset with the infrared LEDs that are needed to illuminate your eyes, they get quite warm after some time. So after you've been doing this for about half an hour, you might want to have a break just because it's getting a little bit too warm. And of course, this was a prototype, and people have requested that there's a little bit more customizability in terms of like changing color maps, changing transfer function, these kind of things. Some of them were deliberately not implemented in the prototype because we wanted to be everybody to be on the same page without too many tweaking options. And of course, creating entire lineage trees should be possible. So at the moment, as said, this is just for creating single tracks. And what's interesting is that users always decided for a speed of around showing 4 volumes per second. So meaning you see a new volume every 250 milliseconds. And interestingly, this is exactly the onset time for a smooth pursuit. So people seem to intuitively settle for the time that they actually need to focus onto something. No, focus is not the right word, but to stick your gaze onto something and follow it. And another interesting thing is that people also had the liberty to decide on the scale that they wanted the data set to have in the virtual reality space. And people have often settled for about human scale. So they scaled the data sets, kind of a cubic data set, 2 meter side length. This was approximately the size that people have decided for. And this is also a quite interesting aspect, because in the real world, you usually have a feeling of how big things should be. There are these kind of visual tricks where you have forced perspective and you show like a car in front of a house, but it's actually a toy car and these kind of things, because your brain knows this car is about like 4 or 5 meters. In virtual reality, and this is actually a little bit under-researched at the moment, when you show objects that don't have a like well-defined size scale, it's not yet totally clear what people settle for. And therefore, we find it quite interesting that everybody has kind of settled for the same size data sets. Okay, and here are some further results from the user study. We have evaluated these kind of things on a Likert scale, where people could grade the question on a 0 to 4 scale, where 0 means fully disagree or 4 means fully agree. And you can see that the people all agreed that the software felt responsible to their inputs, that it also felt for them quite natural and intuitive, that the cell tracks that they were able to create looked reasonable to them, which is also a very, very important and interesting question, because all of them had never used such an interface before. And they were able to complete the tracking task with confidence. And they also universally agreed that the technique provides an improvement over current techniques. And as I mentioned before, we also did the evaluation in terms of this task load index. So people were asked, for example, how mentally demanding was the task, where we achieved kind of a medium score. Physically demanding, it was scored rather low. And this is actually interesting, because what people are used to in cell tracking is like, moving around the mouse, being stationary at your desk, not actually moving in any way. Now here you suddenly use your entire body to follow cells around, and people nevertheless did not find this strenuous. They also were happy with the pace this was executed with. They were successful in this is actually a mistake. So sorry, I didn't correct it in the graph. So this one is actually supposed to be here. This is the one where the scale is the other way around. So no, this is unsuccessful. I actually corrected it. Okay, so no, then this is actually correct. So people were actually quite successful in accomplishing what they were asked to do, and they only had to work kind of medium hard to accomplish this level of performance, and were not really like stressed, insecure, or discouraged. Okay, so summary. So we all know that cells and nuclei are quite difficult to track. Manual curation is often necessary, but quite painful. And in this bionic tracking approach, we have replaced the manual point and click tracking with an eye tracking based approach, where essentially your entire body becomes the user interface. And with this approach, we have been able to create cell tracks quite reliably and quickly. The approach has been accepted by the users, was found nice, and we have also shown a clear benefit in terms of ergonomics and speed. And it's also interesting. This is, I think, one of the few practical applications of eye tracking in volumetric data yet. There's only one other one that I've found, and this was just on geometric data, so like mesh data. So this is also quite a nice innovation. Okay, and with that, I would like to thank you for your attention and for having me. And with that, I'm done.
Thank you for a great presentation. That was super
actually, I'm not done yet.
Okay, please go ahead.
So I think some of you who are doing statistics, they might have already gotten a little bit angry with me before when I was talking about the user study. So we have some certain limitations here that we still need to work on. So user study with 7 people, like a lot of people in the HCI community would strangle me for that. The problem is this study was intended to be kind of a proof of concept thing, which it has fully fulfilled. But we had planned up a follow-up study, which was supposed to take place in like early to mid 2020. You can imagine how that went with the necessity of putting VR headsets on multiple people. So this did not happen. And also, I was just talking about single cell tracks, but I think biologists are usually interested in tracking more than a single cell. So what do we do about that? And now I actually have to take a little bit of a detour. And I'm sorry if I already got you excited for being done. So this will take a few minutes more. So the entire thing I've been showing you, this entire software has been built on top of a visualization library that we have developed that's named Scenery. And we have also developed ImageJ and Fiji-based front end for it that's named SciView. And the people shown here, Kyle Harrington, Tobias Peach, and Curtis Rüden, they're 3 of my long-term collaborators on this project. Is actually, so SciView actually yesterday had its 5th birthday, so it takes amazingly long to develop these kind of software pieces and bring them into use, and we have even not yet published a paper about it. And so this entire bionic tracking thing is based on Scenery, because we have their virtual reality, we have the eye tracking things in there. And there's a little bit of a distinction between the 2 software packages. So Scenery tries to bring into the mix a kind of user and developer friendly API. You can render things on a desktop, on a VR headset, and on distributed machines like Cave System, for example. Crucially, we do out of core volume rendering based on the amazing big data viewer software that Tobias Peach has created. And it's also cross-platform, so this works on Windows, Mac OS, and Linux. Then SciView brings the entire ImageJ and image analysis things on top with image processing and mesh processing, and also polyglot scripting. So if you want to bring Python, if you want to bring Ruby, if you want to bring R, throw it on there, works. And just to show a few things that we've been doing with this. So on the top left, there's like a kind of mixed mesh and volumetric visualization of segmentations from EM data and segmented neurons. On the lower left, you can see a simulation of neurodevelopment along a morphogen gradient. So this is kind of an interactive, explorable simulation. And what I'm very excited about is what you see on the right. This has been created by our very talented student assistant, Justin Berger. This is like an interactive VR visualization of proteins where you can play around with the proteins, modify them, show side chains, and so on. And this is just very recent work that he sent to me yesterday, so I'm very excited about this. And Vladimir Ullmann, who is also quite well known in the tracking community, he has created another piece of software on top of SciView that is meant to simulate plausibly looking microscopy images from physical principles. So here we have kind of a in silico Drosophila embryo. And his simulation software is actually written in C++ and communicates over 0MQ with our software on the JVM. And it's agent-based simulation, and we can send commands both ways so they can talk to each other, and we get this nice equilibration of the cell nuclei here. And now there is a little bit of an elephant in the room. So we have this tracking software, and there's a ton of tracking software already out there, right? There's like there's TGMM, there's like TrackMate, there's Mastodon, there's Mammut. And we thought, okay, let's actually not reinvent the wheel, but let's team up with the Mastodon people. So these are, again, people you've already seen in my presentation today. There's Jean-Yves Tineves and Tobias Peach, who are spearheading the Mastodon project, and Vladimir Ullman is involved as well. And our current goal is to bring the bionic tracking approach into Mastodon so people can actually use it. So it's not just, a research prototype anymore, but something that's actually usable for people. Because research prototypes are kind of a cool thing, but what often happens is, PhD student comes, builds cool prototype, leaves, prototype, sits somewhere, nobody uses it. Another PhD student comes a few years later, is frustrated by the old code, and so on. We've probably all been there. So our goal is not just to provide like research prototypes, but actually to put these kind of techniques into use. And by teaming up with the Mastodon crew, we are hopeful that we can actually do this soon. And recently, we had a very talented PhD student join us, Roshan Lan, and she has been working on the integration of Mastodon with SciView. So you can actually get like volume rendered VR images combined from Mastodon into SciView. You can see like the 3D context of what's going on in your tracking. Synchronization works both ways. When you change something in SciView, it changes in Mastodon, and the other way around. And you can see here that Roshan is moving around the detections in the Mastodon window. They are automatically adjusted in the SciView window as well. I will skip ahead here a bit. We can change the spot size. So this is actually going pretty well, and you don't need to have several views of the same data anymore. You can actually put on your VR headset. You can see what the cells are doing within their natural environment, so to speak. And the next step is to put the bionic tracking approach on top of that. So we can actually use that directly inside Mastodon and put that into people's hands. Okay, so, and as you can imagine, and this is the second elephant in the room, this time quite literally, going through a lot of cell tracks manually is quite a pain, and it turns into a combinatorial nightmare when you say, okay, I have the cell, it divides, and it divides again, and then you are at the Drosophila embryo with 10,000s of cells, and you're like, damn it. Now I got to track that manually or what? No, nobody does that anymore. So you do an automated approach, but you need to seed it somehow. So we have also recently teamed up with Co and the Elephant team. And Elephant, if you have not heard about it, it's a cell lineage tracking tool that works by incremental deep learning. So you can continuously feed it with manual tracking data, and it improves its cell tracks on the fly. So what we're now doing is we put together Mastodon, Elephant, and bionic tracking. So we get online informed incremental deep learning in virtual reality informed by eye tracking. This is kind of where we want to go. And I hope that we can soon put this into people's hands. As said before, we had some troubles now, of course, because of the pandemic with organizing user studies. And because of that, we want you to upgrade. So if anyone is interested in being our guinea pigs, our plan is that we can maybe get a few headsets with integrated eye trackers that we can send out to people and let them play with it for a few weeks and then give us feedback. The feedback aspect for us is crucial because still like this user testing and, you know, dragging 20 people through your lab and having them all use the same VR headset is still like a little bit shady. So we think that by maybe giving this to people for like a few weeks, we can also get some interesting data out of that. Okay, and in terms of future work, so we definitely need more user testing and quantitative comparison with ground truth data. This ground truth data has actually been created by Vladimir Ullmann and his team in the context of the cell tracking challenge. But for that, we actually need an entire lineage tree, which is why we go down the entire rabbit hole and put that into end user software, because this is the easiest way for us to actually get entire lineage trees out of that we can then compare. So we are already in the process of sticking this together with Elephant, and maybe we can even add segmentation on top of it, maybe with Stardust or another algorithm that works quite reliably. And as said, the integration with Mastodon is now already ongoing. And as you can imagine, and I hope I have already made that more than clear, this entire thing is, of course, a team effort, right? So I would like to put out a big thanks to all the people who have been involved with this. So the original Bionic Tracking team with whom we built the paper together, that's Kyle Harrington from the MDC Berlin, Raimund Dachselt from TU Dresden, the Interactive Media Lab Dresden, and Ivo Spalzarini, who was my PhD supervisor at the TU Dresden and the Max Planck Institute for Molecular Cell Biology and Genetics. Such a long name. I always, when I was there at the phone, this was horrible. I could never spell it entirely. And of course, I would always like to thank the Scenery and Salvia crew, Giuseppe, Justin, Ayaman, Luke, Roshan, Debo, and Jan. And of course, our cell tracking heroes, Toby Peach, Jean-Yves Tineves, Vladimir Ullmann, and the all-around hero of the ImageJ community, Curtis Rüden. And now no more jokes. Now I'm actually really at the end. I think I filled the time halfway.
Thank you very much. That was
thank you.
Really great. Do we have any questions for Ulrik? Yeah, JK, do you want to go ahead with the question?
Actually, several questions.
Oh no.
Okay, so one is, so from what you showed, it was basically ab initio tracking, but you also mentioned actually correction. So is there a way of basically reconciling tracks? How would that work?
So this is not done yet. As said, what we've done so far is kind of the research prototype that we've used to kind of demonstrate the principle, and that it's kind of accepted by people. And what you've just mentioned are exactly the things that we now want to do with integrating this into an existing cell tracking software, such that you can actually correct tracks that have already been created, that you can feed new tracks into an automated software, and so on. So this went much beyond the initial prototype. And I can tell you, so this project I've been working on for several years. I have shelved this and pulled it out of the shelf again for probably 3 or 4 times in the beginning, just because eye trackers were too expensive. And then the pupil people came around. It's like, yes, finally we can do it. Then I couldn't calibrate them. And that took me another year probably. And then finally it worked at some point. It was absolutely horrible. So, but I'm happy that it worked at some point.
Yeah. And my second question relates a bit more about the architecture. Like our modularity. So there are 2 things I'm thinking about. One is about you mentioning the integration of machine learning, deep learning stuff. I mean, in practice, we don't use just one. And we have had projects already where we move between, let's say, elastic and cell pose, or Stardust and cell pose. So it would be cool to not be limited to one that is already built in. And the other thing, on the other side, when you were talking about the cell tracking software. So for example, Arivis already has a VR thing that I've actually tested.
Yeah.
It would be very nice if those things were compatible in some ways.
I entirely agree with that. And in terms of kind of the exchangeability of different, let's say, plugins, right? So we already extensively use the entire SciJava plugin infrastructure that's available from the Fiji side. So the way we are building this is modular. So if you want to exchange pieces, that will be possible.
Yeah.
So we're not trying to lock people into our own thing, but it should be interoperable. That's kind of one of our priority goals.
And finally, my last question, let's say, is also related to some of the things I'm doing at the moment. Is how feasible would it be to stream this over the network? Because some of the compute might sometimes be a bit heavy, and so you might want to have that a bit in your data center or something. And not on a local machine.
So there have been great successes recently with, like, for example, game streaming, right? There's like this Xbox, what did Microsoft call it? I forgot, but Google Stadia, for example. So games are possible, right? And you can do that with a low latency, and that works well. In VR, this is a little bit more complicated because VR is super sensitive towards latency. And we are actually working on something like that, but I can't tell you too much about that yet. But it's of course this problem we are aware of, and we are at the moment exploring different possibilities, especially when it comes to like this rendering large volumetric data over the network.
Thanks.
Yeah, I hope I can tell you more in a few months.
Okay. Thank you.
Good. Thanks.
You're welcome.
Faber, do you also want to ask a question?
Yes. Thanks a lot for the nice talk. I was wondering how the biometric tracking works when users looking at dividing cells. So they have two options, right? They can follow the one or the other daughter cell. And if you then compare the results of the different users, how would this work?
You know, this is easy. You just go like, you know, this. No, so we actually play a trick here, and I would love to take credit for this one, but actually this idea came from our biologist friends. We don't do divisions, we only do fusions. You know, we play the data set backwards.
Okay.
So you don't end up with this problem that you have to, because you know this puts additional mental strain on the user, right? Imagine you are in the situation, oh, I want to do this tracking, I want to be done in 5 minutes. You follow the cell divides. What do? This is a quite stressful situation for the user. So we get around that entirely by just, you know, playing it backwards, and then it fuses, and then you can say at some point, okay, this is now the cell division event, and done.
Okay. Thanks a lot.
It's a very cheap trick, but it's quite effective. Thank you.
That's very clever. I think, do we have any other questions from the audience?
Okay.
Okay, so we have a question.
Okay, there's one in the, I mean, maybe I can read it. It's in the chat
great.
here. Yeah. So Maria Kugle from Spain asks, she's wondering whether there are differences in tracking between people of different ages and people with normal eyes and those with myopia or eye problems, and how reliable and reproducible the tracking data will be then. So this is a very interesting question. So at different ages, we haven't really investigated yet. So I can tell you about the age bracket of our tests. So our youngest user was 27. Our oldest user was 39. So this was a quite age discriminatory study. And of course, you would need to do that with more people in the future. When it comes to myopia, for example, a lot of the VR headsets are actually able to adjust for that, either by changing the lenses or by just moving them around. And even if you have myopia, if your glasses do fit inside the headset, then it just works as well as if you're looking at real life data. And when it comes to reproducibility, this is a problem that is not just plagues our approach, but that actually the cell tracking challenge people around Vladimir Ullmann also had, because give people a data set to give 5 different people a data set to track, and you will end up with 5 different results. So nobody will exactly produce the same tracks, but there's of course like a you could, for example, imagine like having a heat map or something where people mostly agreed or disagreed. And that's actually also an interesting point, because if you then think about automated approaches, you could say, okay, where are the things that we want to improve? And you could probably introduce some uncertainty metric on your automatic algorithm, and then with the bionic tracking approach, improve just these areas where the algorithm says, yeah, unsure about that. And yeah, so reproducibility, as said, this is a issue in general in tracking. And with reliability, we didn't have any issues. So some of the participants in our study were actually myopic, and they didn't report any negative any issues with that. So I hope this was answering your question.
Great, thank you. Claudia, did you also have a question?
Yes, I actually also have a question along these lines. If you are having, if you're looking at cells that you have labeled with different fluorophores, for example, and you have different cellular structures that might distract the viewer in the eye tracking, do you have to look at these and do the tracking in individual channels, or have you any experience with that?
We actually haven't done multi-channel stuff yet, but my assumption here would be that you would probably want to do this by channel, depending on. So if you've labeled like wildly different things, so let's say a membrane marker and a nuclear marker, right? You would look in entirely different places. Then it would make sense to show them separately. But if you just want to do like cell tracking, right? If you just want to know where did this go, then you would probably anyway just focus on one channel and follow this one around. I think this very much depends on the exact task, and I think we would also not want to, put the user into a no choice scenario. So I think in such cases the user should decide by themselves what they actually want to see. And this is actually one of the things that has been criticized in the study, that we had a limited selection of what people could change. But as I mentioned in the talk, this was actually by design, so we could put people for the moment at least on the same page and not have too many variables you would need to account for.
JK, did you want to add something?
Yeah, actually related to you are looking for people to try.
Are you volunteering?
Not myself, but I'm thinking of volunteering or finding volunteers around here.
Sure.
Because I think there are projects that could benefit from that.
So
but that's my question, basically. Would that involve our data or your data or both? I mean, how would that work?
So I said we are still figuring out the exact logistics of that. Ideally, of course, we both want something from that. So what you would probably need to do is like do something with our data set, so we have something to compare with. Yeah. And of course, you can also use it for your data sets and try to see if there's any issues with it and so on. I will actually put my email address in the chat. So you can reach. You're welcome to reach out. I would be very excited to help out.
Yeah, I will look around, and because as I mentioned, we have people who've used the Arivis VR for tracking, so that could be a nice complement.
Definitely.
Great. So I hope maybe also some other people can consider testing this out, because it sounds like an interesting but also a really fun way of doing cell tracking. So maybe then with that, as we're running a little bit out of time, thank you very much, Ulrik. That was a super fun.
I actually forgot one slide. Can I still show that?
Yeah, sure, go ahead.
Sorry. So it's actually important because, advertisement. So is it stuck now? All of the things we do are open source. So actually, the prototype software of this is available if you want to have a look at it. It's really alpha stage. So if you wanna try it out, please let me know. But if you want to try out the SciView stuff that I've shown, the repository is at this URL. And there's also documentation available at this URL how you can install it on top of Fiji. And that is really, and you know, Pinky promised this is really my last slide.
Thank you, but that's really important. Open access is great, and that people can try out these
exactly,
things.
exactly. And we also have a GitHub channel, so if you want to come have a chat, do so.
Great.
Thank you very much. This was great.
Again. Yeah, thank you for the great discussion as well, everybody. And I just want to briefly mention before handing over to the Tech Exchange that we'll be starting next week a new series within the virtual pub format. This is together with the Cumulus program, which I think most of you will know. And this series will be all about correlated imaging and combining different imaging technologies. And so and this will happen on every third Friday of the month, actually until next year. So we have a really great schedule lined up, really combining all sorts of different technologies. And next week, we'll start off with a talk from Ori Avinoam from the Weizmann Institute in Israel, and he'll be telling us about correlative light and electron microscopy at room temperature and methods for correlating the two imaging modalities there. And we hope you can join us for these talks for this new series as well. Okay, and with that, I think we can wrap up the virtual pub part, and I hand over to Claudia for the Tech Exchange.